In this lesson, we're going to talk about a single population mean using the student t-distribution. So let's first do a quick review and tie it into last lesson. So the previous lesson, we talked about how we can calculate a confidence interval for a single population mean when we know the population standard deviation using the normal distribution, or on the calculator, we could use the z-interval. So for estimating means, when we know the population standard deviation, we found our confidence interval by taking our point estimate, which in this case, since we are trying to estimate the mean, we would use the sample mean as our point estimate. That's our x bar. And we would add and subtract the error to give us our interval. So that's when we did this by hand. Now, in order to get that error, we had a formula. And the formula was that we found our z critical. And then we multiplied that by our population standard deviation, and then we divided by the square root of the sample size. So once we found out what that error was, we could take our sample size and add and subtract that error to give us that interval. When we did this on the calculator rather than by hand, we used the function on the calculator called z-interval. Okay, and then the last thing we talked about is that sometimes researchers are going to know a specific confidence level that they want to be at within a specific margin of error. And so when that happens, we can figure out the sample size needed by using this formula. We take our z critical and square it, and we multiply it by our sigma squared, and then we divide by the error squared. So this is going to give us the desired sample size. So when we know sigma, we use the normal distribution our z's to figure all this out, to find our z critical, our interval, etc. So now let's look at what happens when we don't know the standard deviation. And this is what happens in most of the cases. It's usually the case where you don't know what the population standard deviation is, so you're required to use the sample standard deviation in order to make an estimate for your sigma. And the normal distribution only works well when you're finding confidence intervals if you know sigma. But if you don't know sigma, then and you use S to estimate it, then the normal distribution doesn't work out so well. So when you don't know sigma and you're trying to estimate the mean, then you want to use what's known as the student's t-distribution. So the student t's distribution looks like a normal curve, although the wings on each of the ends are a little bit thicker. When you find your t-score rather than z-score, that means pretty much the same thing. You're just using the t-distribution rather than the normal distribution, but that t-value will tell you how far away from the mean you are. When it's standardized, of course, your mean is going to be 0, just as the normal distribution. And then the shape of the t-distribution really depends on what's called the degrees of freedom. And the degrees of freedom is basically just your sample size minus 1. The larger that sample size is, the closer the graph gets to looking like a normal distribution. And so those wings are going to get thinner and thinner and tail out. When we use the t-distribution, the way that you find your t-score is you can use inverse t on your calculator to find your t-critical, just like you do for your z-critical. We would use t-interval rather than the z-interval on our calculator when we use the calculator method. Your error is very similarly calculated. The only difference is you're going to take your t-critical times your sample standard deviation divided by the square root of n. So if you want to calculate your error by hand, that's how you can do it. And then you still create your confidence interval by taking your point estimate and you add and subtract the error in order to get that interval. So a lot of this is the same. You're just going to use a little bit of a different formula and you're going to use a different calculator function, but the idea behind it is the same. You add and subtract your error from your point estimate so that you get that interval. I've got two examples that I want to go through with you. The first one, I'm going to go through and show you how to do it by hand, and then from there we're going to use the calculator method. And then I've got a few examples where the examples are mixed and you have to figure out whether you're going to use z-interval or t-interval to determine the confidence interval. And that way we can practice recognizing the difference between the two. So the first example says, a hospital is trying to cut down on emergency room wait times. It is interested in the amount of time patients must wait before being called back to be examined. An investigation committee randomly surveyed 70 patients. The sample mean was 1.5 hours with a sample standard deviation of 0.5 hours, and we're going to find the 95% confidence interval, and we're going to round all answers to the nearest hundredth. So let's pick out the important pieces here. We have that there are 70 patients, so n is 70. We have that the sample mean was 1.5. We have a sample standard deviation of 0.5, and these are in hours. And we want to find a 95% confidence interval. Okay, so here's all the information we have, but I want you to pay attention to the wording here. Notice how it says it's a sample standard deviation. We don't know what the population standard deviation is in this problem, which tells me I'm going to use the t-distribution rather than the z-distribution, our normal distribution. So the first thing we're going to do is we're going to calculate this by hand, and then we're going to do it on the calculator and compare our answers. In order to do our calculations by hand, the first thing we need to find is our t-critical value. So if this is our graph, just a quick sketch, our mean is in the middle, that's our x bar, and our sample standard deviation is 0.5. We want to be 95% confident, which means 95% is going to be in this middle, and we want to find these values here. So what we're going to do is we're going to find t-critical by working backwards. I want to find t-critical by using standardized t, which means my mean and my standard deviation is going to be 0 and 1 respectively. So I'm going to put in my percentage. Now I know my percentage here should be 2.5% on the wings because in total it should add up to 100% underneath that curve. So I know 95% is in the middle, so there's 5% left over, and split between the two wings, it would be 2.5 each. So from my percentile, I'm going to put in 0.025. Then what I have to do is put in my degrees of freedom. So my degrees of freedom, remember, is the sample size minus 1. So I'm going to label this as DOF for degrees of freedom. Since our sample size is 70, the degrees of freedom is going to be 69. So I'm going to put in my degrees of freedom for 69, and then I'm going to figure out what my T critical value is. So let's go ahead and do that on the calculator. We're going to go to the distribution list, and I'm going to hit second vars. And here's where we do inverse norm. That's to find our Z critical. Now to find our T critical, we're going to use option number 4. I'm going to put in my area to the left, and my area to the left is 0.025 for 2.5%. I put in my degrees of freedom was 69. I'm going to hit enter and paste it to the home screen and hit enter. And I'm going to get negative 1.99. Now, typically when we're looking for the T critical or the Z critical, we're not worried about the negative, just looking at the number itself. So we're going to use that our T critical is 1.99. Usually for the critical values, you round to 2 places. Okay, so to find the error, our formula is our T critical times our sample standard deviation divided by the square root of our sample size. So we got our T critical was 1.99. We're going to multiply that by our standard deviation, which is 0.5. And then we're going to divide by the square root of 70, since that's our sample size. Now, when we put that in the calculator, we're going to round. I'm going to round it to 4 places. We get that our error is 0.1189. That's our error. So now to find our confidence interval, I'm going to take my point estimate and add and subtract the error. So when I take my point estimate and I add the error, that's going to give me 1.5 plus the 0.1189. That's going to give me 1.6189. When I take X bar and I subtract my error to get the lower end of my interval, I'm going to take 1.5 minus the 0.1189. That's going to give me 1.3811. So now our confidence interval is going to go from 1.3811 to 1.6189. This is our confidence interval. So I would say for my final answer, my interpretation, I would say we estimate with 95% confidence that the population mean wait time is between 1.3811 and 1.6189 hours. Okay, so that's our interpretation. Now, that was doing it by hand. If you want to do it on the calculator, so let me come back up here and make a note. On the calculator, you would go and use T-interval. And then because of rounding, our answer that we did by hand is probably going to come out slightly different than what the calculator gives us because we were rounding. However, it should come out pretty darn close so that we can see that we did it right by hand. So let's go ahead and do that now. So to calculate our T-interval using the calculator, we're going to go to the Stat button. And I'm going to arrow over to tests. And then we're going to scroll down. And the last section, when we use the normal distribution, we use z-interval. That was option 7. In this section, we're doing t-interval. So we're going to hit option number 8. And then we have 2 ways that we can calculate this. If we had a list of the actual values, we had the data, we would enter that information into our list, and then we can tell the calculator which list to use to calculate this confidence interval. Because we have the statistics and the information given to us in the problem, rather than the data, I'm going to scroll over and I'm going to make sure that my stacks is highlighted. I'm going to hit enter, and then I can just enter that information. So under the X bar, I'm going to put 1.5 because that's my sample mean. Under my sample standard deviation, we had 0.5 for that. Our sample size was 70. And we did a confidence level of 95%, so we want to put that in as a decimal as 0.95. And then I'm going to go ahead and hit the calculate button, and it should come up on your home screen with all the information. And you can see that the confidence interval from the calculator is 1.3808. That's our low end of our interval, and then the high end of our interval is 1.6192. Now, when you compare that to what we got by hand, it's pretty darn close. We got by hand 1.3811, and we got 1.6189, so it's pretty close. In the next example, it says, suppose you do a study of acupuncture to determine how effective it is in relieving pain. You measure sensory rates for 15 subjects with the results given. We're going to use the sample data to construct a 95% confidence interval for the mean sensory rate for the population, assumed to be normal, from which you took the data. So this is the data. It says it's assuming that it's normal, which means we know it's going to be that bell-shaped curve. However, we don't have the population standard deviation. And when we use the sample standard deviation to make that estimate, sometimes that doesn't come out right. So we're going to use the t-distribution. And we need to know some information if we're going to do it by hand. By hand, we need to know the X bar. We need to know the sample size. If you count the values there, you'll see that the sample size is 15, which means the degrees of freedom is going to be 14 because that's one less. And we also need to know the sample standard deviation. So the X bar and the sample standard deviation, we can put that data in on the calculator and get that information when we do one variable stacks. When we do one variable stacks, we get that the X bar is 8.2267, and we get that the sample standard deviation is 1.6722. Okay, the next thing that we need to know is our t-critical. Okay, if we're going to do a t-interval, we need our t-critical. This is going to be a 95% confidence interval. So I know that this area here is 2.5%, and I know that this area here is 2.5%. So I'm going to use inverse t to find my t-critical. So I'm going to put in my percentage, which is 0.025, and my degrees of freedom, which is 14. When I do that on the calculator, I'm going to get that my t-critical is 2.14 if we round it to 2 places. Okay, so now using this to do it by hand, I'm going to find my error first by taking my t-critical, multiply it by my standard deviation of the sample, and then divide by my sample size square root. Okay. When I put that in on the calculator, I'm going to get 8.924. So then to find my confidence interval, I'm going to take my point estimate, which is my sample mean, and I'm going to add and subtract my error. My sample mean is 8.2267. So when I subtract my error, I'm going to get 7.3. When I take my X bar, or my point estimate, and I add my error, I'm going to get 9.15. So I know my confidence interval is from 7.3 to 9.15. Now, when I write my interpretation, I'm going to write that we estimate with 95% confidence that the true population mean for the sensory rate is between 7.3 and 9.15. So that's our interpretation. Here's our confidence interval. Now let's go ahead and do this on the calculator. So to calculate the t-interval, I'm going to go ahead and go to my stat button, and I'm going to go to edit. And since we have the data for this, you should go ahead and enter the data. I already have mine pre-populated in here. However, pause the video for a minute and put your data into your list. And then I'm going to show you how you can use your data directly to find the confidence interval. Once you have your data in your list, make sure you know which list you put that data in. Then we're going to go to Stat again and over to Tests. And we're going to go down and tell the calculator for option 8 that we want to calculate a t-interval. Now this time, since we're going to use data, I'm going to scroll over and click on the data and make sure that's highlighted. And then you want to make sure under list that you tell the calculator which list you have the data in. And then leave frequency at 1. Don't touch that. And then, of course, put in your confidence interval. And then you're going to hit calculate. And then the calculator will give you your X bar and your standard deviation all at the same time if you need it. And then it gives us our high and low value for our confidence interval. We got 7.3006 and 9.1527, which is pretty close to what we got when we did it by hand. Ours is a little bit off because of rounding, but that's pretty typical. And then from there, you can, of course, make your interpretation. Now, if all you had was the t-interval and you don't know what the error is, then remember, you can figure out what your mean is by finding the midpoint of your high and your low value. And then you can figure out the difference between your mean and either the high end or the low end of your interval. Let's go ahead and practice that. So if all we knew was that the confidence interval was 7.3006 to 9.1527, if that's all the information we had given by the calculator, then what we can do to find the mean and the error is the mean is going to be in the center. So remember, when we look at our picture, the mean is always in the center, and then our interval would be 7.3006, and then on the other side I would have 9.1527, and we would have 95% as our area in the middle. So if I want to find that X bar, since we know it should be in the middle, I can just find the midpoint of my two endpoints of the interval. So to find the midpoint, I take my 7.3006 plus 9.1527 and divide by 2. That will give me my x bar. So using these values, I get that my x bar is 8.2265. Now it's slightly different than what we got when we did the one variable stacks to get that x bar, but it's pretty darn close. It's just due to rounding. And then once we get the x bar, I can figure out what the error is, because the difference between the x bar and either of the endpoints, that distance between them is my error. So I can take 9.1527, that's this high endpoint, and subtract 8.2265 to get my error. And that gives me an error of 0.926, which is pretty darn close with what we got when we did it by hand. In the next few examples, we're just going to go back and do a mixed review of what we've learned so far in this chapter. So that way we can identify what the important information is and what kind of interval we're looking for. So in the first example, it says the American Community Survey, ACS, part of the United States Census Bureau, conducts a yearly census similar to the one taken every 10 years, but with a smaller percentage of participants. The most recent survey estimates with 90% confidence that the mean household income in the United States falls between $69,720 and $69,922. We need to find the point estimate for the mean, and we also need to find the error bound for the mean. So the only information that we have is our confidence interval. So if we look at our confidence interval, it's going to be 90% confident. And on the left side, our low value is 69,720. We know our mean is in the center. And then we have our high value, which is 69,922. And if we want to find our point estimate, we need to find our midpoint. So we're going to take 69,720 and add it to 69,922 and divide by 2 so we can find the midpoint. When we do that, we're going to get 69,821. So that's going to be our x bar, or our point estimate. Now to find the error, if we know what the center is, this is my center, I just need to figure out what the difference is, and it doesn't matter which value I use, that will give me my error. So I'm going to take 69,821 and I'm going to subtract my low value, which is 69,720. That's going to give me my error. That will give me 101. So that's our error, or the book calls it our error bound for the mean. The next example says that unoccupied seats on flights cause airlines to lose revenue. Suppose a large airline wants to estimate the mean number of unoccupied seats per flight over the last year. To accomplish this, the records of 220 flights are randomly selected and the number of unoccupied seats are noted for each of those flights. The sample mean is 11.1 seats and the sample standard deviation is 4.16. And I forgot to write this in here. We're going to do a 92% confidence interval. Now, if you read the information, what's given to us is the sample size. We're also given the sample mean. We're also given the sample standard deviation. We do not know sigma. We do not know the population standard deviation, which means we are going to do a t-interval. So we're going to put in our sample mean, our sample standard deviation, and our sample size and do t-interval. If we round it to two places, we're going to get 11.12 and 12.08. So our interpretation of this would be that we can estimate with 92% confidence that the mean number of empty seats for the population is going to be between 11.12 and 12.08. For the next example, it says, suppose that a committee is studying whether or not there is a waste of time in our judicial system. It is interested in the mean amount of time individuals waste at the courthouse waiting to be called for jury duty. The committee randomly surveyed 81 people who recently served as jurors. The sample mean wait time was 8 hours with a sample standard deviation of 4 hours. So the information that we have is that the sample size is 81, our sample mean is 8 hours, and our sample standard deviation is 4. We do not know sigma. We don't know the population standard deviation, which means, again, we're going to use t-interval. Now, if we want to do this for 95% confidence, we're going to put in that our sample mean is 8, our sample size is 81, and our standard deviation for the sample is 4. We're going to put all that in there, and we're going to get that our confidence interval, when we round it to two places, is 7.12 and 8.88. So our interpretation of this would be, we estimate with 95% confidence that the mean population wait time for jury duty is between 7.12 hours and 8.88 hours. In example 4, it says a pharmaceutical company makes tranquilizers. It is assumed that distribution for the length of time they last is approximately normal. Researchers in a hospital use the drug on random sample of 9 patients. The effectiveness of the tranquilizer for each of the patient in hours is as follows. So we are given the data. It was not given to us that we have the population standard deviation. This is unknown. We don't know what sigma is. So what that tells us is that we have to use t-interval. Now we don't know what the sample mean or standard deviation is, but we can figure that out from the calculator, either using one variable stacks or when we go directly to do the t-interval. I would suggest to do it all in one step. We can do t-interval, and we can just use the data option on that. And we're going to create a 95% confidence interval. So we're going to put all the data in one of our lists. We're going to choose the data option, tell the calculator which list the data is in, and tell the calculator that we want to do a 95% confidence interval. And what we're going to get is a confidence interval that is from 2.27 to 2.76. Now, the last example says, suppose that accounting firm does a study to determine the time needed to complete a person's tax forms. It randomly surveys 100 people. The sample mean is 23.6 hours, and it has a known standard deviation of 7 hours. Now, that doesn't say that it's the sample standard deviation. It's saying that this is a known standard deviation. So this is our sigma. We have that the sample mean is 23.6. So what that tells me is, because we know what the population standard deviation is, for this one, we can actually use the normal distribution, we can use our z-interval. So I'm going to put all this information in on the calculator. I'm going to use a 90% confidence level. And when we put all this information in, I'm going to get a confidence interval of 22.449 to 24.752. So we can use a z-interval on this one with 90% confidence because we know what the sigma is.